Hey everybody, welcome back to another round of physics, and yeah, let's get going. Today we are going to merge some of our past discussion, namely that involving vector fields and integrals, and combine those concepts together in an idea called flux. Now, first off, I should tell you, like verbal definition, if you will, the flux. What this represents is the amount of a particular vector field crossing a particular area. Now, I know that's rather vague, but the reality is that this concept is very useful in multiple fields. And so, in this example or in this class, we'll be dealing with the flux of the electric field or the flux of the magnetic field. Other places you might be dealing with, for example, the flux of a velocity field or the flux of, maybe a temperature gradient, something like that. So I'll leave it very generalized for the moment, and then we'll see in the next lecture, we'll take it down into a specific for this class. Now, mathematically speaking, how we take this definition and turn it into an equation, you can think of it like this. It is the dot product of a vector field, here indicated by the letter U, and an area element, delta A. And then we have a couple of other notational issues. For example, we know that there's three ways to multiply vectors. Number one, we multiply vectors by scalars. Okay. We also have multiplying vectors by another vector, either by the dot product or the cross product. Here we have the dot product in particular. And because it is the multiplication of two vectors, we somehow have to indicate the direction of, put in quotes, the direction of the area. Now, we use the letter N to represent this. And what N is it is the direction normal to the surface. Outside of that, the flux is represented by uppercase phi, and I will tend to subscript it with whatever vector field we happen to be dealing with. So, for example, the electric field I'll subscript with E, or maybe the magnetic field I'll subscript it with a B, etc., etc. Now, I've written it in kind of finite elements, but you could alternatively write a differential equation, namely a small infinitesimal flux is given by the dot product of your vector field into a differential area. Again, notationally speaking, sometimes, and it depends on what book and who you're talking to, sometimes you might see the area be given a vector symbol. And really what that means is the small scalar area times the normal. Now, as I previously hinted at, there are various ways you could think about this flux, and it comes into play in very different parts of physics and engineering. Here, I like to think of this. Me personally, I always think about sunlight going through a window, and then you can talk about the flux of the solar radiation or light through a window. You could similarly say, hey, what about the flux of light on a solar panel? And again, you're trying to think about how the vector field is coming in, represented by light, and the area of your window or the area of your solar panel. I always also think about, like, if it's raining and I'm in the middle of the desert and I'm carrying around my coffee cup, you could think of the flux of rain into your coffee cup. The surface of the opening represents an area. If I'm in the middle of the desert, I'm going to want to orient my coffee cup not sideways. You'll notice that then the direction perpendicular to the surface is this way. Presumably the rain's coming down. And so when I have my coffee mug oriented in a poor direction, no rain or no vectors cross that area. Similarly, for example, something like fluid flow or windmills, you again can think of the flux, there's a velocity vector field, and because of that velocity vector field, it is carrying along, for example, particles of water or molecules of air, then the flux is related to the amount of material that passes, say, through an opening or passes through the cross-section of the windmill. Good. I will note, because this is a dot product, you'll notice that there's 3 different ways for you to change the flux. You can change the magnitude of your vector field. You can change the magnitude of the area. Or, good, you can change the relative positioning between the vector field and the area. So, just a brief overview of the dot product. Again, from a graphical interpretation, if you are given 2 vectors, A and B, the dot product between A and B is related to the magnitude of A, the magnitude of B, and the angle between those 2 vectors. Now, if I associate, say, for example, the cosine of A, if I associate those 2 together, that piece is, so I'll pretend A is the hypotenuse for a second, and you see that cosine gives you the adjacent leg. So A cosine of theta would be represented by this length in green. And you notice that the dot product has the overall effect of finding the component of A that is parallel to B, and then of course multiplying those 2 values. And this is the reason why I sometimes state that the dot product is finding the overlap of 2 vectors. This is particularly pertinent when you're talking about the when you're using unit vectors. And you say, well, Greg, why did you choose to associate the cosine with A? I didn't have to. It turns out that if I associate the cosine with B, and we'll get this in a different color, if I associate the cosine with B, then I end up finding this blue length, right? I think about B as being the hypotenuse of a triangle. I'll drop it, and here you could think of this blue section as being B cosine of theta. And it turns out it doesn't matter if you find the component of A parallel to B and multiply, or you find the component of B parallel to A and multiply those 2 values, you end up with the same number at the end of the day. Lastly, for a notational issue, sometimes you will see some books reference B cosine of theta as being B parallel. So I'll put in a definition there. Or similarly, you might see A cosine of theta be written as A parallel. Now, I usually refer to that as kind of the geometric definition. What we're really dealing with are how the vectors are oriented in space, and namely, we need to know the angle between the 2. But you could also do this algebraically using the vector triplet. And you're already familiar with that in terms of how we've been doing a lot of magnitude calculations, and a magnitude is also just doing a dot product. And so I have this for completeness written for you, where the subscripts represent the x, y, and z components. A couple notes about n. We've already said that the n hat is the direction perpendicular to the area that you're considering. Now, if you're dealing with, say, a 2-dimensional area, in other words, say something like a flat plate, okay, you could think of n as, you have fielder's choice. Okay? You could think of n as pointing downwards, and you notice that that's perpendicular to the surface beneath. But you also have a choice of n being perpendicular to surface, pointing up. Okay? And for these types of surfaces, I'll call it an open surface, you are perfectly free to choose whichever direction you want. It won't affect the underlying physics. The big issue, and you already know this, once you choose a direction, you must stay consistent with it. And this in particular will be important when we're dealing with a topic called Faraday's law. We will also be dealing, particularly for the next video, in closed surfaces. And by closed, I mean that you have some sort of two-dimensional area that you're considering, but it encloses a volume. And in that situation, n hat must be perpendicular to the surface, but also pointing away from the interior. Let me give you an example. If we have a cube, okay, you'll notice, of course, that the surface of the cube represents an area. And because I am considering all 6 faces of the cube, that area encloses a volume. In this situation, because it is a closed surface, we choose n hat by convention. You say, why is this? It's because we had to make a choice, so by convention, we choose it to point outwards. And for this particular surface, you'll notice that there's actually 6 different n hats. For example, the n hat on the right face points to the right. But for the top surface, it points up, and etc., etc., etc. So you can pretend that there are different n hats depending on which surface we're dealing with. Shouldn't be much of a surprise. I guess for completeness, I'll put this one back here. And we will, if you would like to find the total flux through that surface, you will be required to look at each individual n hat. Now that's for a situation where there are 6 different surfaces, but you could imagine some surface that is continually curved, which means that there are many different n hats. For example, a sphere. And again, you could think of each of these little segments of the sphere has an n hat pointing in slightly different directions. And so finding the flux through the surface of the sphere will require you to consider each of those individual directions. And that, you can see, is where the integration process will come into play. Here for the cube, for example, we have a finite number of n hats. But here on the sphere, we will have to divide the surface into infinitesimal patches, each one with its own normal direction. We'll find the flux through each of those patches and then add them up. So I know that's a pretty short video, but that's pretty much all I have for today. And what we'll see is that the next video, we will take this idea of flux, this concept of flux, and we are going to specifically apply it to the electric field. It turns out there's some interesting results. I can't say that they're always going to be useful, but they're certainly interesting. And the other aspect of this is that it gives us an opportunity to start using some of those integration things that we've talked about and start getting a little bit more comfortable with playing with these vector fields while doing integrals. So that's all I have for today. I thank you for your attention. Keep up the good work. I'll see you next time.